All right, so we think that many of the iron asteroids started out much larger than they are right now, including Ceres, Vesta, and I mean Vesta actually has evidence that there's parts of it that are missing, um, and so it's collisions, lots of collisions inside of the asteroid belt, which really mimic the things that happened in the overall solar system, right? Especially in the inner parts of the solar system. The inner parts of the solar system, there's lots of evidence that there were lots of collisions in the early parts of in the early days of the solar system. All right, so now this is an interesting phenomena because think about where the asteroid belt is. It's between Mars and Jupiter. Okay, so here's Mars, a little more than 1.5 astronomical units. Here's Jupiter, a little more than 5 astronomical units from the sun. And so, but inside of the asteroid belt, there are actual gaps where you don't really find a lot of asteroids. So and these are what are they called? Oh yeah, there it is right there. The Kirkwood gaps. Kirkwood was a guy an astronomer who originally noticed this. And so the Kirkwood gaps are caused by resonances with Jupiter's orbit. So what happens is as Jupiter orbits the sun, what would happen is if there were some asteroids like right here in this gap, in this Kirkwood gap, let's say, as Jupiter orbits the sun, it would cause these asteroids that would have originally been there to migrate and clump in these regions. And then there's this other gap. They're like whole numbers multiplied by the orbital period of Jupiter. That's what causes these gaps. And it turns out, of course, that's the same reason that Saturn, the rings of Saturn have certain gaps, right? Because of the resonance the resonances with some of the moons of Saturn, in particular, of course, Titan, right, the largest moon of Saturn, it causes there to be gaps in the most famous one, of course, is the Cassini gap in the rings of Saturn. All right, so it really has to do with the orbit of Jupiter. The Trojan asteroids are too loosely swarmed. Uh, they're basically, you find them about 60 degrees in front of. This is not a really good picture here, but about 60 degrees in front of the orbit of Jupiter and 60 degrees behind the orbit of Jupiter. As I mentioned before, the points. So as any planet, by the way, any planet orbits the sun, there are 2 points, 60 degrees in front of the planet, 60 degrees behind the planet, that form. There's actually five different regions, but the 2 that are 60 degrees in front and 60 degrees behind the planet, these are points that orbit with the exact same period as the planet does. They're called the Lagrange points. So there's one point that's between the planet and the sun, one point on the opposite side of the planet compared to the sun, and then one on the opposite side of the sun compared to where the planet is. So those are what are called the Lagrange points. They're actually very useful. For example, we have a satellite that if you put it at L1, the Lagrange point number 1, which is between the Earth and the Sun. You don't have to supply it. You don't have to supply that satellite with any fuel anymore, right? It'll like if you think about the the satellites that are in orbit around the Earth right now, occasionally they have to get a boost to stay in orbit, right? Because there's even in space there's a little bit of atmosphere, a tiny little bit amount of atmosphere, and that will cause a drag on the planets or sorry on the satellites, and eventually drag them back out into the Earth's orbit, or into the Earth's atmosphere, which you don't want that for a satellite. But if you get to these Lagrange points, you once the satellite is there, it doesn't ever need any more fuel. It'll just stay there forever, essentially. The other Lagrange point that we use all the time, is it's on the opposite side of, so you take the sun and the Earth, the opposite side of the Earth from where the sun is, and that's called L2, and in fact that's where we have the James Webb Space Telescope. That's exactly where we put it, because it's about what is it, about 1.5 million kilometers from the Earth, so it's out well beyond the orbit of the moon, and once a spacecraft is there, it just continues to orbit in the same period as the Earth. All right, so that's doesn't matter whether it's a satellite that humans sent or just a natural satellite. These Lagrange points. All right, so there are some other satellites. Asteroids. We're talking about asteroids, which can be satellites as well. But at any rate, there's these what are called NEOs, the near Earth objects, and of course, if you think about it, this is obvious why these are important. Because if they cross the Earth's orbit, we could crash into them. And there's lots of them. There's over 10,000 of them that have been identified. And actually, I should mention this. So with Jupiter, back in the 1990s. So this is the kind of the origin of why we're looking at this in detail. In the early 90s, what was it? 94, I think it was 1994. There was an asteroid that, or I'm sorry, it was a comet. It was a comet that broke up, and it was called Comet Shoemaker-Levy 9. It was the ninth one that this team of Shoemaker and Levy found. And what was unique about that asteroid is that it was going to crash into Jupiter. We had worked out the details of it, and we knew that it was going to crash into Jupiter. And nobody knew, what was going to happen. They thought, maybe we'll be able to see that from Earth. But in the summer of 1994, every telescope on the planet was on our planet was aimed at Jupiter to get a look and see what was going to happen. And indeed, this satellite, this comet broke up, and there were, I think, over 20 different impacts, and each impact left an actual mark in the upper atmosphere of Jupiter, and some of those marks stayed around for like a month or so, so there was this huge impact, and it was the first time. I mean, we certainly knew before that, at least in our heads, we knew that objects hit other objects in the solar system, but that event in the mid 90s, basically, the fact that the general public got got to see this, from the vantage point of all the telescopes on Earth, looking at this event and showing, that this huge planet like Jupiter could actually have scars, at least, temporary scars, from this incredible impact, got people thinking about, hey, what about objects hitting Earth? Maybe we should start paying attention to that. And there were even Hollywood movies that were made. They weren't very accurate or anything, but we're humans. The human race kind of concentrated on the the potential of something hitting the Earth, and so several years after the comet Shoemaker-Levy 9 collided with Jupiter. People on the Earth decided to start looking very specifically for these objects that cross the Earth's path, and so we actually put up, or not put up, we devoted telescopes that actually every single night look for these near Earth objects. So they're concentrated on the night sky, and they're just always looking for objects that cross the Earth's path. And like it says here, there's over 10,000 of them that have been discovered. We don't think any of them are going to come and hit Earth within the next century, at least. And it turns out that's like the best you can do, because some of these things are so small that the light from the sun, right? The sunlight that's always heading out into the solar system, will actually slightly affect their orbit, and if that's the situation, we can't always predict what's going to happen. Because the amount of light that hits these things can cause them to, like, if let's say they're made of ice, right? So if these objects have ice inside them, the light could actually start to melt the ice, or even turn it into gas, and let's say it's a little asteroid and it has a little gas coming off of it, that can actually alter the orbit of the object, right? And so it becomes unpredictable. It becomes difficult to actually predict where this thing is going to be, because you don't know what direction that gas is going to come off, and direct this little asteroid. So we're constantly monitoring these things with surveys that are looking every single night out and trying to make sure that the asteroids are where we think they are, and none of them are going to cross the Earth, right? And cause mass extinction like it did 6 million years ago to the dinosaurs. There could be even dead comets, where these things will keep traveling around the sun, but not dead. Just means that there's no more ice, so that there's no tail when the comet passes close to the sun. Most of the comets will just as they go around the sun, eventually they just kind of die off, and all their material is vaporized and turned into this vapor, and of course, if that vapor passes through the Earth's orbit, that's in fact what the meteor showers are, right? That when there's certain times of year where you look up and there's a whole bunch of meteors coming from a certain direction. All right. Anyhow, we'll get to that shortly. All right. So what we're going to do now is talk about what are called the Kuiper Belt objects, and Pluto turns out to be one of the largest of the Kuiper Belt objects. It was discovered in the year 1930 by a guy named Clyde Tombaugh, who was looking for